So we're now going to state and prove Roleless theorem. This is, in a sense, a baby version of the mean value theorem, and is considered a stepping stone towards proving the mean value theorem. So sometimes this is called Roleless Lemma. So let's look at the statement. So f is assumed to be continuous on AB and differentiable on the open interval AB, and f at A and f at B are the same. So, I mean, this is what I need, but sometimes it's convenient to put 0 here, just to make the drawing easier. It doesn't change anything really. But if you have all of this, the point is that there exists a C in the open interval AB such that f prime C is equal to 0. So let's make a drawing here. So what happens is that you have A here, B here, and then the function starts here, ends here, is continuous in between here and differentiable. So, well, maybe looking something like this. And then the point is that whenever your graph is continuous, differentiable, and starts and stops at height 0, then at least some point in between exists so that the derivative is 0. Okay, so you have a stationary point. And of course, when we say that there exists such a point, we mean there exists at least such a point. So here we see another candidate, another candidate, another candidate, and yet another candidate. And also please note that putting f of a and f of b equal to 0 is not important as long as they're equal to each other. So if both were up here, starting and ending at the same height, and then doing something in between, then for at least one point in between, I have a stationary point. Let's now look at the proof. Now, this theorem can be proven in a bunch of different ways, but usually you do a proof by cases. And to prepare for this, we're going to use the Min Max Theorem. So the Min Max Theorem, since f is continuous on a closed and finite interval, implies that there exists points u and l in AB such that f of x is smaller than f of u and bigger than f of l for every x in AB. So this, in other words, is the global minimum of f, and this is the global max. So these two exist. And now we proceed to a proof by cases. So case 1 is what? Well, case 1 is if both u, l are endpoints. But this implies that f of u is equal to f of l is equal to 0, since this is the value I have at the endpoints. What does this mean? Well, this means that this is a 0, this is a 0. So this means that f of x satisfies this inequality for all x in AB, which means that f of x is equal to 0 for every x in AB. But this means in particular that f is constant, so the derivative of f is 0 at all x in the open interval. And this means we're done in this case because we were required to prove that there exists at least one point in this interval so that the derivative is 0. And we have proved here that the derivative is 0 at all points in the interval. So here we're really done. What about case 2? So case 2 is what remains, and this is at least one of u and l is not endpoint. What does this mean? So, well, we have two cases, either u or l, but it really doesn't matter. So say u is not an endpoint, so u is in the open interval AB, but f was differentiable on AB. So this means that u is a global maximum of f at an inner point where it's differentiable. So this implies by Fermat's theorem on stationary points that f derivative u is 0. And we're done, because now this u here works as my choice of C. And of course, if L is in AB, then by the same reason, f derivative at L is equal to 0. And if we look at the drawing, then this all makes sense, since we basically pinpointed this point here, so the maximum, or this point here, so the minimum. Or if the max and minimum were both here, then the graph was flat, so the derivative was 0 everywhere. In any case, we are done.